streaming. Okay. And go back to the browser. There we go. And we'll take a look at the test itself, and then I'll write the answer right next to the questions, and you'll kind of share that also into the shared folder. So this way you can study if you want to. You can actually use it for studying. The final exam, I can tell you, is going to have mostly material after the second exam. So it might have something that is still related, like proofs, the techniques to prove something, but still be important. So let's go to. Yeah, this is the second exam. So what I'll do is I'm going to make a copy of this first. So let's go to here and make a copy. And this is the copy, which is where the answer is going to be. All right, question number 1. Yes?
Do you have like an exact date?
For the final? Yeah. It'll be the same date that is scheduled on the schedule. I cannot remember what it was. I believe I have it on in the syllabus too, so you might want to check that. Is it the 15th? Okay. So question number 1 is, I thought it is pretty related to the questions in the practice test, although this one has 1,000,000 bits instead of 4 or 5 bits, okay? But it's still asking kind of the same kind of question, except this one has to do with the binomial distribution as well. Okay, so let's go ahead and read the question first, because it's important to read the question correctly in order to attempt to answer it. So the same thing in the transmitter and receiver configuration, so that part is pretty much the same thing as in the in the practice test. It is known by experimentation that the chances of correcting, transmitting, and receiving an entire packet, okay, and the word entire is in italic, which is telling you that the probability P, it says an error here. I think it has to do with how it is rendered. So when I click it and go in and put a space, it would actually display P correctly. So for some reason, there are certain things that won't render correctly in this particular browser. Could be a Firefox issue, could be something else. But anyway, the probability of transmitting an entire 1,000,000 bit packet is P. It is not an individual bit, it is for the entire 1,000,000 bit packet. Is that okay? So if I were to give it an exact value to P, let's say 85%, so that means there's an 85% chance that a 1,000,000 bit packet will transmit entirely correctly with no error bits whatsoever. Is that okay? All right. You may assume the probability of a 1 transmitted but received as a 0 and the probability of a 0 transmitted but received as a 1 are the same. So this part is different from the practice test, because in the practice test it is asymmetric, but in here it is symmetric. Okay, so a 1 being erroneously received as a 0, or 0 erroneously received as a 1 have exactly the same chances. Is that okay so far? Okay. Furthermore, the probability of transmitting and receiving a bit incorrectly is independent to all other bits. In other words, if you have 3 erroneous bits already so far, it does not change the probability of the next bit being transmitted correctly. Okay? So part A is asking you to explain and derive the expression of a single bit transmitted and received correctly. In other words, once we know the probability of receiving an entire packet, 1,000,000 bits correctly, is P, what is the formula or the expression that will tell you the chances or the probability of transmitting a single bit correctly and receiving it correctly? Yep.
The millionth root of P. The millionth root of P.
It will be P to the power of 1,000,000th.
Yeah.
Yeah. Okay. So this requires a little bit more zooming, because it's a little bit harder to read otherwise. So the correct answer is P to the power of 1 divided by 1,000,000. There we go. Is that okay? Yep.
Could you have written it as like the millionth root of p?
Yeah, you can do that too. I don't know exactly how to do it here. I don't know. I don't know how to do it, using a LaTeX.
You don't need to.
But now I need to know.
Okay.
Root of Q. Okay.
Is this supposed to be showing up in your shared folder?
Say again?
It's supposed
Not yet. I have not moved it yet. So if you want to move it, okay, there we go. So square root, which is this symbol here, and the p is on the outside in square brackets. And then fraction a n, okay. The answer is SQRT. Doesn't look like there's an easy answer to that. So I'm just gonna use the power one.
I think you scrolled past it.
I scroll past it.
Yeah, it was near the top of the first answer.
This one?
Up a bit more.
I think this was
Yeah.
was the question.
At the near the top where it says the bottom of $p, the thing right before it, that expression.
This one?
Up a bit. To the right.
This one?
Yeah.
Okay. So it's still kind of the same, which is a square bracket on the outside. So we'll give it a try. But before we do that, I'll put this one in the shared drive first. So for those of you who want to look at it, you can do that. So we have to move to my drive, 440, 17 spread. Oh, okay. Shared is the same anyway. Okay, there we go. Move it here. Okay, so it should be shared now, except it's called copy of x2. Let me change the name to Spring 17 Exam 2. There we go. So can you see it now for those of you who are trying to access it? Sort of. Okay, I'll let you guys try to do this, and SQRT /SQRT square bracket. I don't know whether this is gonna work or not. So we'll 1, 2, 3, 4, 5, 6. Yeah, it doesn't look like it's gonna work here.
What if you put an open curly brace? 'Cause I think that's what it had.
Now the curly brace is
No,
for the
uh,
other stuff.
The curly brace after the bracket ends, since that's what it had in the answer, I think.
So it's got the curly brace here, but it has square brackets here.
Yeah, and that makes p root a.
Yeah, but I need 1,000,000 with that. I don't think Google document can do this, but the other one works just fine. So we'll just kind of stay with this one. So it's p raised to the power of 1 divided by 1,000,000. Is that okay? That's the chances of transmitting and receiving a single bit correctly. Is that part okay? All right. So because this number is really going to be useful, I'm going to give it a name. We'll just call this Q, because otherwise I have to rewrite this thing over and over again, which is not going to be a lot of fun. So the explanation, okay, if you want an explanation, it's basically P is the chances of receiving 1,000,000,000 bits correctly. 1, 2, 3, 4, 5, 6. And if Q is the probability of transmitting and receiving 1 bit correctly, then the probability, then P, okay, I'm going to insert the equation here. So then in that case, P is going to be Q raised to the power of 1,000,000, right? So because P is Q to the power of 1,000,000, then when you need to figure out Q given P, then you have to raise P to the power of 1 divided by 1,000,000. Is that part okay? All right. Okay, so once we figure this out, then we have part B. Part B says, explain and derive the expression of the probability that a 1 million bit packet contains 1 to 3 error bits. The position of the error bits is not important. Now, every time you see the position of something is not important, that should trigger your thinking process of saying, okay, do we use combination? Because combination means the position is not important. Permutation means the position is important, but combination means it is not important. So now you have to basically figure out, okay, so let's take one first, okay? So 1 error bit in 1 million. Okay. What is the probability of a single packet being transmitted with 1 single error bit, but all the other bits are all correct? What is the probability of that? So we'll start with this one. We already know the chances of a single bit being transmitted and received correctly is Q, and I need 999,999 of those bits that are transmitted and received correctly. And then we have 1 single bit that is received incorrectly, which has a chance of 1 minus Q. Is that okay? So the probability of this by itself, okay, without factoring, but the error bit can be the first one, can be the second one, can be the third one, and so on. Without taking that into consideration, this probability is going to be Q to the power of 999,999 times 1 minus Q, because that's the 1 bit that is transmitted or received incorrectly. Is that okay? But then there are many ways to come up with this combination, because you have 1 million bits, and each one can be incorrect. But I said that the position is not important. So you have to add all of those things together. So that means, oops, I just deleted one too many. There we go. So that means the probability of 1 error bit regardless of position is going to be what? It has to do with combinations. So you have a choose. So how many are we choosing from? 1 bit out of 1 million. That is correct. So 1, 2, 3, 4, 5, 6. We're choosing out of a million a single bit. Which one is the incorrect one? And then you multiply this to Q to the power of 999,999 times the 1 bit that is received incorrectly, which is a chance of 1 minus Q. This is a part of the binomial distribution. It's just that we usually don't play with number that big, which is a million in this case. But it's the same idea. Is that okay? So that's one part of the answer. We're not quite done yet. Okay, this one is actually pretty easy. Having only 1 single bit that is incorrect. But then we have to worry about, what about 2? Well, if you look at this equation here, that one is not too different, okay? So it's Q to the power of 999, Q to the power of 999,998 times 1 minus Q to the power of 2. Because you have 999,998 bits that are transmitted and received correctly, and then 2 bits that are received incorrectly. So this is the chance of one single sequence having exactly 2 errors. But how many sequences can have exactly 2 error bits? Those 2 error bits can be the first 2 bits, can be the last 2 bits, can be the first and the last, right? So how many ways can we have one out of 1 million bits that there are exactly 2 error bits? how do we express that? What do you think? Yep, 1 million choose 2. So it will look like this, except the 1 is replaced by a 2. So now this equation is going to be, it has 1 million, 1, 2, 3, 4, 5, 6. Choose 2 in this case, q to the power of 999, 998, and then 1 minus q to the power of 2. In other words, this expression is telling you, if I don't care about which 2 bits are received erroneously, this is the combined probability. Is that okay? Are there any questions regarding, why we need to have this 1 million choose 2 in front of, q to the power of 999, 998, 1 minus q to the power of 2? Why, there's the choose, or why we need to worry about combination? No questions? That's okay? Okay. So once I explain this one, we can also take a look at a smaller example, because the big example is harder to understand, but when you boil it down to a smaller example, it becomes a lot easier to visualize. So let's look at 3 individual bits, and I'm going to be lazy here. So I'm going to copy and paste it, because all that we are really doing here is changing the 3 over here, and then as a result, change this 8 to a 7, which is the result of subtracting 3 from a million. And then on the second line, we also change this 2 to a 3, change this 2 to a 3, change this to a 7, and then change this to a 3 as well. Okay, so that's basically, when you add up these numbers, then it becomes the actual answer, because each one is only addressing, the first one is only addressing what is the probability of having 1 exact, error bit. Then we have 2 error bits, and then we have 3 error bits. So when you add up these 3, that becomes the actual answer. In other words, the answer is something like this. If I call this A, and then I call this B, and then I call this C, then the answer to this question is A plus B plus C. Is that okay so far, or not? Okay, so if this is not, clicking, because it's hard to visualize 1 million bits, and all the different ways to have 2 bits out of 1 million, you can make examples that are easier to visualize, okay? So to make an example that's easier to visualize, you can just downsize the problem a little bit, okay? So now we have a packet of, choose something that's really small, okay? 5 bits, okay? 5 is probably good. And we have exactly the same situation. So now you have to say, okay, out of a packet of 5 bits, what are the ways that we can have 1 bit of error out of a sequence of 5 bits? Okay, so let's X represent the bit that is incorrect, and O to represent a bit that is correct. Okay, so you can have the first bit being erroneous, you can have the second bit being erroneous, you can have the third bit being erroneous, fourth one being erroneous, or the last one being erroneous. So these 5 are representing the 5 different ways of having a single bit that is incorrect. Okay? But what are the chances of each one happening? Well, the chances of each one happening is going to be q to the power of 4, because that accounts for the bit received correctly, times 1 minus q, which is the chances of the 1 bit received incorrectly. Is that okay? Then you look at the 2 bits, right? So 2 bits is going to be a little bit more. I'm not sure I can actually enumerate all the possible ones, okay? But we can try. Okay, then you have, it's not too bad. I suppose I can enumerate all of those. Okay, and then we have, oops. To be more systematic. and we have the last one being that. So those are all the different ways of having two erroneous bits. And each one is having a chance of q to the power of 3 times 1 minus q to the power of 2. But then how many of these do we have? Well, we got 10 of these, because it is 5 choose 2. Is that okay? And then of course, if you want to add 3, then you have another bunch. What do you think is going to be 5 choose 3, now that we know 5 choose 2 is 10? 5 choose 3 is going to be 10, exactly. Because you just flip all the x's to 0, to o's, and then all the o's to x's. Those would be the patterns of transmitting 5 bits, of which 3 bits are incorrect, or received incorrectly. Is that helping? I mean, because with a smaller number of bits, we can kind of visualize like that. But with 1 million bits, it's much harder. Is that okay? Or do you want to kind of stay on this one for a little bit? Yep.
For the probability, you have to divide the whole thing over by 2 to the million.
If you, well, since we already have, you do not divide it by 2 to the power of 1 million, because we are not counting the frequency. We already know the probabilities of a single bit transmitted and received correctly. So we are not looking at the frequency. We are now going after the exact probability. So this is based on the binomial distribution. Instead of flipping a coin 1 million times and I'm counting the number of heads and number of tails, I'm reassigning the names to transmitting a bit, receiving a bit correctly, and receiving a bit incorrectly. And obviously, if you look at this as a coin toss problem, it is very skewed, because you would want your transmission system to have a very good chance, very close to 1, to transmit and receive a single bit correctly. But nonetheless, it is the same kind of problem. Is that working out okay or not? Yep.
So the answer, what's the probability of 1, 2, 3? It's just all 3 of those probabilities added together?
Yep. But if you get to the individual parts like this, you will get most of the credit already. Okay. The key is whether you can recognize that the combination is important. But this part is important too. If you give me this part at least, that is worth partial credit as well. So every single part is worth some partial credit, but the entire answer is A plus B plus C, where A is the chances of having a single bit regardless of position, and then B is the error, chances of having 2 bits of error or receiving 2 bits incorrectly regardless of position. Okay. Yep.
For the binomial distribution, there's a part after the choose in the formula on the website that says p to the k times 1 minus p to the n minus k, and you don't have it here. Is that the same question that he was asking?
Okay, but in this case, n is 1 million and k is 1, 2, or 3.
Yeah. So I guess I'm just kind of confused, because that's kind of how I answered the question, using essentially taking the fact that you had said everything has an equal chance of being transmitted wrong or right.
Yep.
I put 0.5 to the millionth times that 1 minus q.
So you're basically using 0.5 as q.
Well, as p, and I never
As
actually
p?
used I never actually used it.
Okay. I guess you have the right structure in that case, but it is important that q is a number that is really close to 1. So you'll get partial credit because of getting the structure correctly, knowing which part to the power of 999. But then if you use the wrong base probability, that would still be a part of the wrong answer. Yeah. Okay. So any other issues with this one? Yep.
Because I thought like maybe a number is like each bit, so I thought like it's only 7 bits. Like
7 bits?
So like it's 1 is 1 bit and then 0, 0, 0.
So you thought this is so you thought this is the pattern being
The pattern,
transmitted.
yeah, and so I put like instead of
Yeah,
999 I
that's
put
a good-
7. Like,
Okay, so then it depends on whether you got the structure correctly. So you got the whole structure
Yeah.
correct, except instead of 1,000,000 you used 7. I suppose that will get most of the credit.
I did the same thing.
You did the same thing? How many
Exactly.
people did that? How many people thought there were only 7 bits?
That's what like
Okay. Because I was trying to use like, okay. So I use, here, you can see how I use a comma and then use a dash to emphasize this is a 1,000,000 bit packet. I just did not use English to spell it out.
It's because we had so many of those single bit problems that I was like
we
that.
can, so
I would suggest you guys, to practice, reading, a question a little bit more carefully before you start to write the source code to land another Mars probe. You guys heard about that one, right? Where they got the units wrong. The measurement of units is not consistent. So I guess the retro rocket did not, fire at the right time. So they wasted one Mars probe accordingly. Okay, next time, ask. Okay. Question number 2. Okay, number 2 is really similar in many ways to both practice exams that we have gone through. Okay, the only spin I added to this one, okay, I simplified the algebra part. Okay, so the algebra part of this one is like really easy. But what I did is instead of having the induction to only go in one direction, I have to go in both directions. Because now you have the positive integers and then you also have the negative integers that you have to deal with. So you have to prove both parts, or at least mention similarly, apply this technique to the negative side. Okay, because you cannot just prove on the positive side and assume the negative side is going to work. Okay, so let's go ahead and take a look at this one, base case. Okay, base case is easy. It's still the same thing because according to the original definition, f of 0 is 0. Okay, so that is a very strong suggestion that 0, n being 0 is a good case for a base case. Okay, so when n equals to 0, f of n equals to 0 by definition. Is that okay? So we don't question that. We don't question why that is the case. But at the same time, when n is 0, n is 0 because our proposal is f of x is really just x itself. Okay? So this part, okay, knowing that f of n is 0 is telling me what is the value on the left-hand side. Just saying that n equals to 0 is telling me what is x on the right-hand side, and they're both zeros, and as a result, okay, we prove the base case. Okay, the theorem is true for the base case. Do we have any questions about the base case? How the base case is proven in this particular question? Okay. So the next one is the induction step. The induction step is the tricky one because we have 2 directions to go. Okay. So we have to say induction step. So you have 2 sub cases here. Okay. So you have positive side. Okay. So on the positive side, what you want to say is assume the theorem, or you can just spell out the theorem itself. You can say assume f of n equals to n of it. Okay, I'm going to switch back to x here. Is true for x equals to n. Need to prove the same is true for x equals to n plus 1. Okay, this is for the positive side. So the way to do this, you probably already know how to do it because the algebra part is really, really simple. So you basically say, okay, it's f of n plus 1. By definition is what? This is on the positive side. Okay, so it is f of n plus 1, right? But because of the induction assumption, what do we know about f of n? F of n is assumed to be n, so it's just n plus 1, done. Okay? That's one side, okay? So the tricky part is you have to do the negative side too. Because the induction step is only going in one direction, and the base case is a 0. So if you only have the positive side, then you can use the base case, apply the induction step, and then you can say, oh, it works for 1, 2. And then you stand on 1, right? And then you use the induction step, and then say, oh, it works for 2, 2, 3, 4, and so on. So you can prove that it works for all the positive integers. But what about the negative side? It doesn't do any work. It doesn't help with the negative side at all. So in order to handle the negative side, you have to separate the cases and say assume f of x is true for x equals n. So that part is the same. Now you need to prove the same is true, but the theorem is true for x equals to n minus 1. Okay, that's what you need to do. So f of n minus 1, based on the definition of f, is f of n minus 1. Okay, and that thing is just n minus 1, and you're done. Now, if you only get one side, you will get most of the credit because it shows that you understand that a proof by induction has a base case and an induction step. Is you have to spell out the assumption in the induction step, and then kind of go through the proof, which is a one-step proof. That will get you most of the points. But if you get the negative side too, you will get all the credit for this question. Okay. Are we doing okay on this one? Okay. All right. Question number 3. Question number 3 is closer to the lotto problem than anything else. Okay. Out of 12 there are 12 students out of 37 that who can play a guitar. And there are 12 students out of 37 can play a guitar. 7 students are sitting in the front row of the classroom, and I'm asking what is the probability that at least 3 of the 7 students are guitarists. Okay, that's what the question is asking. Are there any questions about the question itself? What is the scenario that is given to you? Questions? Okay, all right. You may leave your answer as an expression, which means you don't have to come up with the actual value. Okay, so out of okay, the first question is out of 37 students, how many ways can I arrange 7 students in the first row? That's the first question. That's basically our omega. It is the base number that we are dealing with. So out of the entire class of 37 students, and we have 1, 2, 3, 4, 5, 6, 7 seats in the front row, okay? How many ways can I pick students to sit in the front row? First of all, is this a problem that has replacement or without replacement?
Without.
It is without replacement, because I cannot have I cannot have a clone and a clone and a clone of a student sitting in the front. I mean, I'm not going to clone students. Okay? So that means the same student can only occur up to once in the first row. Right? So it is without replacement. Very good. So once you understand this is without replacement, it's a question of is it permutation or is it combination? Did I say anything about the positioning in the front row? I just need 7 students in the front row. Okay, how they arrange themselves in the front row do not seem to be important in this question. So it is without, it's not permutation, because permutation is when sequencing or the ordering is important, and in this case, it is not saying that the ordering is important. So that leaves only one thing, which is combination. I just need to choose 7 out of 37. that becomes the cardinality of the omega, okay? So I'm gonna just write here and say this is the cardinality of omega is we are choosing out of 37 7 students. Okay. So this is important because it is going to be my denominator. My numerator, on the other hand, has to do with, okay, so out of these 37 students, 12 can play a guitar, and the rest, which is 25, do not claim that they can play guitar. And I want to know, the probability of at least 3 of the 7 students can play guitars. So, when you look at this, you can look at it as, exactly 3 students, exactly 4 students, exactly 5, 4, 6, and 7. Okay, and you have to add up all those numbers. Is that okay? Okay, so we'll go ahead and make the problem a little bit easier, and we'll ask the question, okay? How many ways can TAC choose exactly 3 guitarists? And 4 non-guitarists to sit in the front row. That is the question that we have to answer. Because once you figure out this one, the other ones are kind of like, oh, okay, about the same. How many people in the class can play guitar again? The total. 12 people, right? So I need exactly 3 of those 12 people. I don't really care who you choose, okay? But out of those 12 people, I wanted 3 of them. Yep.
Even though the question says at least 3 of the 7.
Yeah, because when it says at least 3, then you can say the next one's going to be exactly 4, exactly 5, exactly 6, exactly 7. Okay? You can also work the other way around, which is, exactly 2, exactly 1, exactly 0, and then turn it around and say 1 minus having less than 3 students being able to play the guitar. So that's a smaller equation, but nonetheless, you still have to work with the structure that we're dealing with here. Okay. So the question now is, how many ways can I choose 3 out of 12 guitarists? I think the question itself spelled out the answer. What was the phrasing? How do you choose, right? Okay, so out of 12 students, I have to choose 3, okay? What about the other 4 students? Well, the other 4 students are non-guitarists. How many students in this class are non-guitarists? 37 minus the 12, which is 25. So now you have to multiply this with the 25 students who are not guitarists, but out of those, we only need to choose 4. Is that making any sense? But when was the last time we saw something like that? The lotto. Because in the lotto, several ways to win, says, okay, out of the 5 winning numbers, you have to match 2. Now, how many tickets, would match exactly 2 of the 5 winning numbers, and then 3 of the non-winning numbers? We saw something like that when we processed that lotto problem. So this is exactly, it's the same thing, except I recasted the problem to use different terms. Is that okay? So this is the frequency, this is the number of ways that I can choose exactly 3 guitarists and 4 non-guitarists to sit in the front row. So once you know this, then you just kind of copy and paste this. Okay. And now the question is, how about 4 guitarists? Well, if I have 4 guitarists, then we have 3 non-guitarists. So now the numbers will just change. Okay, 4 here, and then 3 over here. Is that okay? Now, of course, if you want to use the sigma notation, you can just, kind of generalize the whole thing and say sigma goes from 3 to 7, and then turn, the 3 into a variable, turn the original 4 into 7 minus the variable, and, that summation will work too. Is that okay? So let me see if I can enter that equation. So the number of ways that tech can choose 3, 4, 5, 6, and 7 guitarists out of 7 students in the front row is the following. So I will check to see if sum works in this case. Nope, doesn't like that. Lowercase sum does work. So we have I, which is the number of guitarists going from 3 to 7. And then inside the summation, we basically use, okay, we'll just use choose. So we have choose out of 12, I people who are guitarists. And then we have the remaining 25 students who do not play guitars. And we have to use, we have to choose 7 minus I of those people as non-guitarists. So that number, the summation, becomes the numerator. And then the denominator is something that we talked about a little bit earlier, which is choosing 7 out of 37. Okay, so then the probability of having a row of students, a front row, okay, of students in which there are at least 3 guitarists is going to be, a fraction. And in the fraction, the first part is this summation. And then the denominator is going to be the cardinality of omega, which is the total number of ways to choosing 7 students out of 37, regardless of whether they can play the guitar or not. So that is the actual answer right there. But if you can get to this part, okay, if you can get to this part here, you will get a significant amount of, well, okay, you'll get enough partial credit to pass this particular question. Because that really is the core concept that I'm testing. On the other hand, if you can say, oh, but that's only addressing the case where we have exactly 4 guitarists and 3 non-guitarists, and you remember that, oh, but we have to add up all the other ones, that's, those are more points, and then you remember, oh, but TAC is not asking the number of ways to choose at least 3 guitarists, it's asking about the probability, so we have to remember to divide it by the total number of ways to choosing 7 students out of 37, then you get all the credit. Is that okay? Or not? How many people looked at this question and remember, hey, this is similar to the model problem? Few, okay, very good. Question number 4. I think some people really like this one and some people really hated this one. The people who hated this one, basically said, at least some people told me that they hated this problem because there's no symbols to use. There's no P for probability, there's no, head or tail. It is just, socks, right? So it's a word problem, okay? You just have to kind of present your argument using, sentences, but you have to use the structure of a proof by contradiction, okay? So how do you start with a proof by contradiction? Proof by contradiction. You have to first identify what the theorem is, okay? So what do you think is the theorem? If you just read the question itself, one morning TAC randomly drew 7 socks out of his drawer and did not get a single matching pair. Is that the theorem? No, that's just setting up the scenario, okay? The second part, which kind of states, in a very non-implicit way, use proof by contradiction to prove that, la 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 la. Okay? What do you think that la 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 is? The theorem. Okay? So you have to first identify what is the theorem because you need to negate the theorem first. Okay? So you have to basically say proof by contradiction. We first have to negate the theorem. Okay? In this case, the negated theorem is the following. It's basically saying it is not the case that tag has at least 7 different kinds of socks in its drawer. What is an easier way to say that tag? It is not the case that tag has at least 7 different kinds of socks in the drawer.
Tag has less than 7 kinds of socks.
Yep, exactly. Less than 7 is great. Okay, so the negated theorem is tag has up to 6 different kinds of socks in his drawer. Okay, so for all of those people who negate the theorem and state the negated theorem, partial credit right away. Because that's an important step. Identify what is the theorem and negate it. Okay? Now, if somebody just says, it is not the case that tag has at least 7 different kinds of socks in this drawer, I will still get partial credit. Still give a partial credit because it is still identifying which part of the sentences is stating the theorem itself, and also remembering that with proof by contradiction, you have to start with negating the theorem first. Okay? Now that we have a negated theorem, how can we use this and argue that, hey, but that's not possible. It's going to lead to a contradiction. How is that going to lead to a contradiction? You know it is going to lead to a contradiction, right? I only have 6 kinds of socks, and yet I drew 7 pairs, and there's no matching pair. It makes sense, but how do you prove it? That's where the rest of the points are. Yep. Okay, so now we have a new task, right? The new task is to say that tag has up to 6 different kinds of socks in a drawer cannot be true, right? Is that okay? And what do you do about that?
You can say that drawing 7 different socks and not getting any pairs implies that you have at least 7 socks in your drawer, 7 pairs of socks.
But that means it's a direct proof to the original theorem. That becomes a direct proof. Yep.
I mean, there's 2 things that you can contradict. You can say, okay, if he drew 7 socks, it means he has at least 7 socks in there. And if, the problem seems to be implying that every sock does have a pair, and so if there are just 7 socks and you draw all 7 of them, then it's going to have a pair in there because every sock has a pair, which contradicts the fact that you that contradicts that you didn't get a single matching pair.
Okay.
So that's the first contradiction. The second one is if you do have up to 6, up to 6 different kinds, and you drew 7, by the time you draw the 7th, then you're going to get a pair.
Yep. But that's still not a rigorous proof.
What would make it more rigorous?
Okay, so I'm going to present it here. But what you said is probably, I will count it as a good answer. Yep, go ahead.
Does this relate to the pigeonhole principle?
Yeah, you can use the pigeonhole principle on this one. If you can quote the pigeonhole principle and apply it correctly, I will count it in. Okay? But what I'm going to do is I'm going to have a new theorem to prove. Okay? New theorem to prove. If tag had, only up to 6 different kinds of socks in his drawer, he would have in boldface, right? A matching pair after drawing 7 socks out of the drawer. So I'm flipping it around and just say that, okay, so I need to prove that tag has up to 6 different kinds of socks in a drawer is wrong. Okay? So to prove that that is wrong, then I have to say, if I had only 6 different kinds of socks, then if I draw 7 times, I would have gotten a matching pair already. Okay? So this is kind of like the proof by contradiction of the proof by contradiction. Okay, I'm using it twice. Okay, so in this case, you can basically do the same thing. You can identify the theorem. Okay, so prove by contradiction again. So the negated theorem, in this case, is going to be tag drew 7 socks out of a drawer that has only 6 different kinds of socks, okay? But did not get a matching pair. Okay. All right. So if I do not have a matching pair, I'm holding on to 7 socks, okay? What is that implying? They're all different, right? Okay. So 7 socks and no matching pair means there are all the socks are not matching. In other words, they're all different. They're all different kinds. And why is that a problem? It's contradicting one thing. What is it contradicting? It's contradicting the given, which is saying that if Ted had only up to 6 different kinds of socks, but now we just show that we have 7 different kinds of socks. Okay? So this proof by contradiction is proving that if I had only 6 different kinds of socks, out of 7 picks out of that drawer, I would have gotten a pair. And that indirectly is going back to the original proof by contradiction and say that it is not possible that tag only has 6 different kinds of socks in a drawer. Is that okay? So what I'm looking for in this particular case, if you finish the proof like this, you get full credit. But if you just identify what is the original theorem and what is the negated form of that theorem, you'll get most of the points. Okay, and I'm just asking for just a little bit of description of why that is not possible. It doesn't have to be a formal inner proof by contradiction to get all the points. Is that okay? Yep, go ahead.
Personally, if I were to say have made a variable and then made it equal to one of the sentences, and then went the normal way of like negation of P or Y or whatever, would that still gotten some of
that will still count. You just have to identify, so let's say you use a P to designate the original theorem. Yeah. You have to tell me which part of the question is P.
Gotcha.
And that part has to be correct.
Okay.
Yeah. Okay. So are there any questions about number 4? Questions? Okay. Question number 5. Okay, so with question number 5, a few people ask me what these numbers are for, 931 and 971. Those are the sequences of, how to analyze this program by running the program backwards. In other words, you start with line 9, then you go to line 3, then you go back to line 1, and what is the conclusion about X and Y? The other one is 971, which is going from line 9 back to line 7, back to line 1, and then what is the conclusion about X and Y? Okay? So, and I want you to use proof by contradiction, which means somehow at the end of this thing, we did not get a maximum. Z is not the maximum of X and Y. Is that okay? All right? Okay. Okay, so prove by contradiction again. So you have to first identify what is the theorem and how are you going to negate the theorem. The theorem is stated kind of here. Use proof by contradiction to show that blah, 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 blah. So this is the theorem itself. After executing the following code, X has the maximum of X and Y. So the negation of that is simply saying x is not the maximum of x and y. Okay? So you can say z is not the maximum, is not max xy on line 9. That is the negation of the theorem. Okay? So this is the negated theorem. Okay. So we want to see how that is not possible. Okay? This is not possible. So we have to execute the program backwards. From line 9, we first explore, okay, so let's just say that we came from line 3. Okay? What does it mean when we come from line 3? If we come from line 3, then z has to be, okay, so let me just write it down here. Okay, so I'll go ahead and write it down. Okay, using the 9, 3, 1 path. Okay. So we ended up here on line 9, and somehow I claim that z is not the maximum of x and y. Okay? So there are only two ways to get to line 9. You can get to line 9 either by going through line 3 or going through line 7. Does that make any sense? Because it's a conditional branch with a then and an else branch. So those two branches are the only two ways to get to the end of the conditional statement. Okay? Using the 931 path, that means z has to equal to y, right? Because of line 3. Okay. But line 3 is corresponding to, is it the then branch or is it the else branch of the conditional statement? Line 3 is the then branch, right? Okay. But to get to line 3, which condition has to be true? Okay, I should say, what is the condition x is less than y? Does it have to be true in order for me to get to line 3, or does it have to be false for me to get to line 3? It has to be true. Okay, very good. X is less than y must be, okay, how do we get rid of this thing? True, okay. So that means, using the 931 path, we can establish a few things. We can establish the fact that z equals y is true. We also know that x is less than y, right? If z is y and y is greater than x, that means z is the maximum of x and y. Okay. Z is the maximum of x and y. And this contradicts the negated theorem, which is saying that z is not a maximum. Okay. This contradicts the negated theorem, and we have a contradiction. Is that okay? Sort of? Okay. What about the other path, 971? So 971 means if we went through the else branch, okay? If you go through the else branch, then z is guaranteed to be the same as z, and z is the same as x because that's what we did, okay? So if you go through line 7 to get to line 9, then we know z and x have exactly the same value. So this is because of line 7. But to get to line 7, the condition has to be false, right? So now your conclusion is z equals to x, and x is greater than or equal to y. Wait a minute here. If z is x and x is greater than or equal to y, that makes z the maximum. Okay? Z is the maximum, contradicting the negated theorem. So the key to this question is, whether you can identify, when you execute backwards, whether you can associate, okay, if we go through this branch, z would be the same as this variable, but then the condition is going to be, this condition has to be true to go through that particular branch. Oh, but that means, z is the maximum. What about the other path? Same kind of thing, okay? If you go through the other branch, then z has to be the same as the other variable, but then the condition of the conditional statement has to be false, meaning that z is also the maximum. So that's how we can use proof by contradiction in this case to show that by the time we get to line 9, z is in fact the maximum of x and y. So are we okay with this? Sort of? Okay, so once it, yeah, go ahead.
The comment was really confusing.
The comment?
So the line 9.
Line 9? The comment is really just asking, do we know that z is the maximum of x and y here? It's just a line of comment. It's not doing anything. It's just here to show that this is the question. Do we know that z is the maximum of x and y? Okay. All right. Are there any questions about these 5 questions before we move on and start to talk about recursion and the master theorem and time complexity of algorithms? No questions about this? Okay, so later on, if you guys need to bring back a question or something, let me know and we can revisit this. But for now, what we'll do is we're going to move forward and start to talk about the time complexity of recursive algorithms. Recursion has its own section. So inside recursion, there are a lot of links. You can start reading from recurrence relations, or you can just start with big O notation. So the big O notation, this is actually a picture of the Japanese. This is actually not Japanese. It is a joint venture between a Japanese animation house and an American, production. So, but that's the robot's name is Big O, and that's why I kind of put the picture here because we are talking about Big O, and Roger Smith is this guy's name. So, so in computer science, the Big O notation is used to characterize the time complexity of an algorithm. In other words, we use Big O to kind of talk about the upper bound of how fast the time it takes to execute an algorithm relates to the size of the problem itself. Okay, so it's about the ratio between the size of the problem versus how much time it takes to solve the problem. If I double the size of the problem, does it double the amount of time? Does it quadruple the amount of time, or does it have what is it going to do to the execution time? That's what we are asking. Big O itself is upper cap. In other words, when you claim that f of n is the big O of g of n, you are implicitly saying that this is true. Okay, so let's take a look at what this part is saying. So when you claim that f of n is big O of g of n, what you're claiming is you can find 2 constants. Okay, the constants do not have to be integers, by the way. They only have to be real numbers in this case. So you basically say, I can find 2 numbers, k1 and k2, such that if you throw any n at me, I can establish this inequality. And the inequality really is just saying that f of n is less than or equal to the first constant, k1, times g of n plus the second constant, k2. That's all it's saying, okay? And this is forming the upper bound. So here's an example. The example is if I know exactly f of x is 4 times x squared plus 3x plus 1 plus the log of x. Okay, what can I choose as my g of n? Well, in this case, my g of n, I have a lot of choices. Okay, but the simplest one that I can choose is x squared. Because if I choose g of x to be x squared, then I can find the constants K1 equals to 8, K2 equals to 1, and that will guarantee that anytime you whatever x you throw at me, I can definitely make sure that K1 times g of n, which is x squared, plus K2, which is 1, is always going to be greater than or equal to the original equation, which is 4x squared plus 3x plus 1 plus the log of x. Is that part okay? But what if K1 is going to be a really huge number? It's going to be 20 billion. As long as it is a constant, it's fine. Okay? Same thing with K2. So all I'm looking for is you can find those constants. How big are those constants? They can be gigantic, huge. It doesn't matter. As long as it exists, as long as they exist, then we're fine. We can use the big O notation. But the biggest takeaway with the big O notation is this inequality here. It only has to be less than or equal to, which means f of x in this case is also big O of x cubed. It's also big O of x to the power of 4, and so on. Because big O is only establishing an upper bound. Okay? It's only establishing an upper bound of how fast the function is growing. So you can always use something that's more extreme. Is that okay? Right? Okay. So we can now use the big O notation to define the big omega notation. So let's take a look at this expression here. This is a Boolean expression. It's basically defining what is the big omega notation. If I can establish that f of n is big O of g of n, is exactly the same thing saying that g of n is the big omega of f of n. Okay? But what does that mean? I mean, how is f of n and g of n relating in this case? If I can say that, okay, let me just highlight the portion right here. If this part is saying that g of n is forming the upper bound of f of n, okay? What do you think this part is now saying? F of n is forming the lower bound of g of n. That's basically what it is, okay? You're just flipping it around and saying that, oh, so if big O is telling you what is the upper bound, then big omega is telling you what is the lower bound. Is that okay? So that means, your function, the function that you're trying to model, can be something that is kind of complicated, with all the wiggly, squiggly, and whatnot. Okay, the green line is representing the function. This is representing f of n itself, okay, which is complicated. But what you can do is to say, well, this is really complicated, but I can find the shape. I can see the shape of this curve here. So you can say, oh, here's a blue line. It's really smooth. It's really easy. Okay, but what is the blue line? The blue line is the big omega. So the blue line here is representing g of n, which is a very simple thing like x squared, x to the power of 3, something like that, something really simple. And all you have to do is to make sure that the blue line is always on top of the green line by choosing K1 and K2 so that it is always above. How much above? We don't care. As long as it is on top of the green line, we're cool. Is that okay? So g of n is the big O of f of n in this case. What about the other side? Okay, just establishing the upper bound sometimes is not very helpful. Okay, because all you can say is, oh, the execution time of this algorithm is guaranteed to be less than or equal to blah blah blah. But if you make that really extreme, it's not going to be very helpful. So what we also want to do is to establish a lower bound, which is represented by the red line over here. So we have used g, f, g, so we'll call this h. So this is h of n, okay? So h of n is forming the lower bound of this algorithm. So the algorithm is now known to have a big O of g of n and big omega of h of n. Is that okay? But that can be useless too. You can choose something that is really insignificant and totally pointless as h of n because it is always going to be less than the algorithm. the actual time complexity, use something that is exaggerated for g of n, so it's way, way, way more than the actual execution time. So your upper bound and lower bound is not really informing the programmer of which algorithm to use. Okay? So that's why we also have a big theta. So when you have a big theta, which is this one here, you are basically saying the same g of n is now forming both the upper bound and the lower bound of f. Okay? How can that be the case? Okay, it's the same g of n. So in this case, I'm basically saying, oh, that's not h of n. It is the same thing, g of n, because g of n in this case is big theta of f of n. How is that possible? You choose the two different cases differently. Okay? So with this curve here, the blue curve is using a particular set of k1 and k2. The red curve here is choosing another set. So I will call this k3 and k4. Same g of n in both cases. By tweaking k3, k1 and k3, as well as k2 and k4, I can use the same function, g of n, to establish the upper bound as well as the lower bound of some kind of more complex and kind of squiggly, equation that I don't want to figure out, which is f of n. Now, if you can establish this, if you can use the same g of n to form both the upper and also the lower envelopes of whatever you're trying to model, then you have just found the right, well, you have found the big theta, which is basically a very good way of approximating f of n. Is that okay? All right. So the notation part is what we are seeing on the projector. F of n is big theta of g of n if and only if g of n is the upper bound of f of n and g of n is the lower bound of f of n as well. So the key is just to pick different k1 and k2 for the upper bound, pick different k3 and k4s for the lower bound, and if you can find these four constants, then great. G of n is now big theta of f of n, which is what we really like. Is that okay? All right. Why is this important? We have just talked about the details, we talked about the how, we talked about the what, but why is this important? I mean, when will you actually see these symbols? Have you guys searched for algorithms in Wikipedia? Okay, so you might have looked up binary search, for instance, right? Okay, so let's look at binary search. Binary search, and the first link is a Wikipedia page. And even before we get into the page, you can see it has already summarized. Worst case space complexity is O1, which means how much space does it take. Worst case performance is big O of log n. Average performance is big O of log n. Okay. Now this is really kind of, they use the wrong symbol. Okay, because the worst case is supposed to be big O. The average case, well, I guess they can use big O to form the upper bound. So when we click on the algorithm, you can go to the best case performance, average case performance, and worst case performance, and we are only establishing the upper bound here. Why do you think we're only using big O instead of theta or omega here? Well, okay, big O is kind of important because it cannot be worse than this. Okay, this is the worst. Okay, in the worst case scenario, the performance is big O of log of n, which is when what you're trying to find is not in the array. Okay. What is the best case performance? Why do you think that is big O of 1, which is constant time? What is binary search? You take the entire array, you calculate the index of pretty much in the middle of the entire array, and then you compare, right? What if that is what you're looking for? That means a constant time. Okay? So the worst time is what we are interested in. For the worst time or the worst case performance, is big O of log of n, which means even if what you're looking for is not in the array, which guarantees that that's going to take the most amount of time, it is only proportional to the log of n. Okay, I know we only got like maybe a minute left. Okay, well, actually 1 minute passed already. But the important part here is how many iterations do we need to look for one single record with 8 billion records. So let's say we have a huge database with everybody on Earth in this database, everybody who's alive, okay? And there are about, what, 7 billion people right now, right? So let's call it 8 billion. How many times do you think I have to go through these iterations or compare, make the array smaller, compare again, make the array smaller in order to find that one single person or to confirm that one person is not in the array?
Log base 2 of 8 billion.
Yep. And that's approximately, okay, so very good. We got the right concept. Okay. What do you think is that number, approximately? Okay, 1 billion is, okay, 1 kilo is approximately 2 to the power of 10. So that makes 1 million approximately 2 to the power of 20, which makes 1 billion is approximately 2 to the power of 30. Okay? So 2 to the power of 30 kind of takes care of the billion. We got 8 left. 8 is 2 to the power of 3, which means in 33 comparisons, okay, in 33 iterations, I can confirm that somebody is not in the array. That is pretty fast, okay? But the best part is, if we find some really cool new technology so that the population of Earth can double to 16 billion, the lookup time will only increase by 1 comparison. So in 33 comparisons, I can search for one single record within 8 billion records. By increasing the number of comparisons by 1, with 34 comparisons, I can now find a single record out of 16 billion. That is why the log of n is great. Is that okay? Is that making any sense? So why is that important? What if you choose the wrong one? What if you could have chosen binary search, but then you look at the search algorithm and go like, oh, this is too long, I want to use something shorter, and linear search is much shorter. What's going to be the impact? Your algorithm will take longer, much longer. And how is that going to affect your employment? So you have to think about it that way in order to understand why this kind of topic is important to us, why we are putting this topic into this class. Okay, so that kind of concludes this lecture. So go ahead and read ahead of me. Now that we know that we're going to go after time complexity first. So read the entire thing, and also read the master theorem, which is what we're trying to get to.